All right, guys, happy Wednesday. This one is a little bit of a longer lecture as well, so pop yourself some popcorn, get yourself a nice iced beverage, and let's get going on velocity and time graphs. Don't forget that your final test flight is going to be done the next time I see you in class. Your comparing graphs lecture is going to be nice and short as well, so if you need to start this and then finish it up later, that is okay with me, but just make sure you have everything done by Monday because we will be doing a graphing quiz in class. All right, so let's jump into it. Velocity and time graphs. So this is going to be even more useful than our position and time graphs because we're going to be able to see a little bit more information. So all of our velocity time graphs, the independent variable is going to be time still. So it's along our horizontal axis, and velocity is the dependent variable on the vertical axis. So there are three things that we need to be able to do to analyze a graph for velocity and time. We need to be able to read values off the graph, which we've been doing. That's just your coordinates. Finding the slope of the graph. But then we also need to be able to find the area underneath of the graph. Yay, math! So excited! So these two graphs represent the exact same situation. We have a student walking to school. They go 80 meters south from home, and they're at a constant velocity of 1.33 meters per second. As you can see, our position time graph, we're showing that we are walking at a constant velocity by an inclined line with a constant slope. So our position is increasing steadily with time. Now, our velocity time graph, though, we are keeping a constant velocity the entire time, so it's actually just a horizontal line. So our similarities, the time scale is going to be the same, so our x-axis is still reading the same length. Your units are very similar, so we have seconds, meters, and then meters per second. And positive direction is still the same. So we typically use north and east as our positive directions on a compass, and the positive areas on our graph are the same idea. The difference is that we have our units on our vertical axes are different. So you have either your meters for your position or your meters per second for your velocity. Your position time graph has a positive slope where your velocity time graph has a zero slope. And then we have the position and velocity on the axes and our titles. So if you remember from like literally yesterday, the slope of a position time graph is just the slope of a line, which is our d2 minus d1 over t2 minus t1. And the slope of the position time graph was 1.33 seconds, meters per second south, sorry. And that was the same as the reading on the velocity graph. But our slope on the velocity time graph is zero. So now, while the value is easy to see, what are the units of the slope on a velocity and time graph? So we take our position, we take our, start that over. Hopefully you remember to edit this out. Anyway, so we have our slope is our y2 minus y1 over x2 minus x1. In this case, our y's are our velocity. So our velocity to our final velocity is going to be read in meters per second. And then we're dividing it by time, which is our second. So that's the same thing as multiplying 1 over a second. So we actually get meters per second squared. So the slope of your velocity graph is actually going to give you the acceleration because that's what the units are telling us it is. So we need to find the area underneath the line, so between the line and our x-axis. So our area for our rectangle, which is, and my little laser pointer again, yeah. Nope, it didn't work. Where's my laser pointer? Laser pointer. So this area right down here, we need to find the area of that, and it's just a rectangle, so it's length times width. So we have 60 seconds for our time, times our velocity was 1.33 meters per second. And we end up with 80 meters to the south. So we have our units and then our direction of displacement. So we have to keep that south with it, even though we have no clue what this is telling us yet. So that area that's under the graph is actually going to give us our displacement, so how far we've gone. So let's actually look back up at when we had the two graphs next to each other. So they represent the exact same thing. In 60 seconds, we walked 80 meters. We had a constant velocity. In 60 seconds, we had a constant velocity, which is zero acceleration, and we went 80 meters by calculating how much space is down here below the line and above the axis. So, reading the graph for velocity time graph gives us our velocity. But when we find the slope, that's going to tell us our acceleration or how fast we're moving. And to find the area under the line is going to give us our total displacement. So these are big ideas to make sure that we have straight, because our velocity time graph is very different from our position and time graph. And so you have to remember that this is for velocity. Our position time graph doesn't give us this type of information. We can just read the graph to find our position, and we can find our slope to find our velocity on a position time graph. And our velocity time graphs are going to be more interesting when we're doing acceleration. So over here on the left, this is our position and time graph for a plane taking off. So we've got our nice little curve up here, and it tells us that we're accelerating. But for us to find an instantaneous velocity, we have to do our tangential line and then do all the calculations, and it's so much fun. Or we take our velocity versus time graph for a takeoff, and what it's actually doing is it's going ahead and giving us that velocity slope that we were trying to calculate here, and then we can go ahead and calculate the area underneath of it. So they both are showing us the plane taking off on runway, and earlier we found the position of the plane, but now we are gosh, I gotta edit a lot of stuff out. It's Tuesday afternoon. I'm tired. So earlier we found the position of the plane by reading the position time graph, and we were finding the instantaneous velocity by finding the slope of that tangent line. So using a position time graph, we were able to kind of see that we were going about 65 meters west. It was easier to read, but more accurate to calculate with our velocity and time graph. So we were going to take the area Okay, so we have a couple different things that we're going to look at here. The first is we have our plane taking off. So we saw this in our last section where we're starting at 0, 0, and we see a curve. So we know that we're accelerating, which means that we have a little bit of a tricky time figuring out what's going on here. Our velocity time graph is showing us acceleration because it has a positive slope over time. So our velocity is increasing steadily over time. Now, to find out what was going on at a certain time to get our instantaneous speed over on our position time graph, we have to draw a tangent line and then kind of connect the dots and calculate our slope of the tangent line to find our instantaneous velocity. Now we can find an instantaneous velocity. So like at 5 seconds, we were going 25 meters per second west. So now we're going to figure out what this little spot under here is telling us. So this is pretty much what I just said, but you can feel free to pause it and write down anything you need. Okay, so we're going to find the position of the plane after 5 seconds. I'm going to go back to those graphs. After 5 seconds on our position time graph, I can go up and be like, it's like 64.5 meters west-ish. It's not quite halfway, but whatever. So while that's pretty easy to read, it's not as accurate as we need. So what we're doing over on our velocity time graph is we're actually going to find the area of it. So going back to our velocity and time graph, if I find the area from 0 to 5 seconds, because I'm trying to find the position after 5 seconds, I draw that 5-second line straight up until I intersect with my actual graph line, and then I find the area within there. So this whole area underneath would tell me my displacement over that 8 seconds, but I'm only looking at the area up to 5 seconds. And that's going to tell me what my displacement or what my new position is after those 5 seconds. So my area of a triangle is 1/2 base times height. And so I fill in my base is the 5 seconds, and my height is at 25 meters per second west. So then I can calculate more accurately that my position or my area under that line was 62.5 meters west. So they come really close to being the same answer, but obviously we're going to be way more accurate when we can, do more math. So we're going to now find the instantaneous velocity at 7 seconds. So to find the instantaneous velocity at 7 seconds on a position time graph, we have to go over to 7 up here and draw a tangent line to that one point, and we intersect at 6 seconds and 90 meters, and also 8 seconds and 150 meters. So then we calculate the slope of that line with our rise over run, and we get that our velocity is 30 meters per second west. Then if we're trying to find our velocity at 7 seconds on a velocity time graph, we go over to 7, we go up, oh hey look, 35. So we got different answers from both of these. And the reason for that is our velocity time graph is going to be way more accurate because it's going to legitimately just easily point us to what's going on. Over on our position time graph, we're going to have to calculate based on a line that we draw that may or may not be the most exact line. So while we can do all these things with both graphs, the velocity time graph is just going to give us a lot more information, and it's going to be easier for us to have the accurate, correct stuff as we need. So both position and time graphs and velocity time graphs can be used to easily find the position and velocity. That's what they're there for. Acceleration is easier to find on the velocity time graph. And in this case, our velocity time graph is linear, so we have a straight line. So that means that our acceleration is constant. Our velocity is increasing at a constant rate over time. So if we're going to find the acceleration of the plane using this velocity time graph, we're going to use still our slope, but we're going to replace it with whatever variables we have on our x and our y. So our acceleration is our velocity at the end minus our velocity at the beginning. So we have 40 meters south, or 40 meters per second west minus 0 meters per second west. And then our time at the end minus our time at the beginning. So our 8 seconds minus 0 seconds. And we end up with 5 meters per second squared west. So our velocity time graphs can be used to create position time graphs and vice versa. So we're going to do a complete analysis of the velocity time graph and then use that information to transfer our velocity time graph into a position time graph. So we're going to look at this graph, and it says the velocity versus the time for a turn. So what is happening here? Well, on a velocity graph, remember that our slope indicates our acceleration. So we're going at a constant pace. Then we have a negative acceleration. And negative acceleration is just our way of saying that we're slowing down. And then we're going at a constant acceleration again, but it's negative this time, which means that we're just heading in the opposite direction. So here we are, our velocity graph is showing us that we're going at 20 meters per second east. Then we have a negative acceleration, so we're slowing down, and then all of a sudden we're negative. So our negative velocity in the east direction actually turns into a positive velocity in the west direction. And that's all right there, if that's easier for you to write down than what I said. So now we're going to look at the velocity of the object after all these time intervals. So we're going to look at each time section here. So our velocity after 10 seconds is 20. After 20 seconds is 20. And we're just going to keep going through that whole thing and filling in our chart. So you'll see here that there are some points where we just can't determine what the exact velocity is. And that's because we have this line decreasing but not intersecting all of our points. So we give an approximate. If you're ever using an approximate for a quiz or a test, please make sure to include this symbol. It's right next to the 1 on the keyboard. So what's our acceleration of the object between 0 seconds and 30 seconds? So from 0 to 30 seconds is this segment right here. And we have a 0 slope. So we have a constant velocity, meaning that we have 0 acceleration. Now between 30 and 90 seconds, there's definitely something happening. So we have to do some calculations to find the slope of that line. So we're going from our ending point at a negative 20 meters per second east minus our positive 20 meters per second east. And then our time difference was 90 seconds minus 30 seconds. And we end up with an acceleration of 0.6 meters per second squared, but it's negative, so we flip our direction to say that we're heading in positive acceleration in the westward direction now. And then from 90 to 160 seconds, again, we have a 0 slope, meaning that we're going at a constant velocity, so our acceleration is 0. So what's the significance of the point at 60, 0? So that's at 60 seconds, and our velocity is at 0. So what is happening there? That's where we're just changing direction. So because that velocity is reading as 0, it's not that we really stopped, it's that we're kind of turning around where we're heading. So our velocity is no longer positive, it's heading towards negative. So to determine the position, we have to find the area between the graph and the time up to that specific point. So it's easier to find the areas of different sections of the graph and then add them together afterwards. And the graph can be broken into 4 sections easily. But we want to remember that the area is negative if it's under the time axis. So make sure that you're keeping an eye on your units, or your positive, negative, there's a word for that. Okay. So we're going to break this up into 4 different pieces based on shapes that we already know what our area equations are. So our first section, A1, is a nice little rectangle. Then A2 gives us a triangle. These are both positive because both numbers are positive, so we'll have a positive area for that. And then A3 is a triangle before we head into A4, which is another rectangle. And because these have a negative value in them, they are going to end up being negative when we solve for it. So we're going to go through and I will kind of slide through these real fast to keep my time short, but please feel free to write down the area equations and solutions as we go, because you will need them later on. So A1, there's A2, A3 is going to be our first negative area, and then A4 is also negative. So now we need to use those areas to determine the position of our object. after so many seconds. So because our first segment, I guess we'll just put it over here, was from 0 to 30 seconds, we are saying that our position when our time is 30 seconds is area 1. So the position at the time of 30 seconds is equal to the area of section 1 that we created, which means that it's equal to 600 meters east. Our next area section ended at 60 seconds. So the position of when our time was at 60 seconds has to be area 1 plus area 2, not just area 2. Remember, we're taking the whole graph into account. We just split it up for math because it was easier. So we have our 600 plus our area 2 is 300, and we get 900 meters east. Now, when we go to 90 seconds, our position when time is 90 seconds is A1 plus A2 plus A3. But remember, A3 was a negative number, so we have to keep that negative with it as we go, and we get 600 meters east. The other way you can do this is you can actually just write it as our position of our time at now 160 seconds is the same thing as the position of our time at 90 seconds plus our new addition. So you can either add each of the areas together, or you can say, I already calculated this one. I'm just going to add in the last area now. Either way is completely correct and accurate. Remember again, this one was negative, so we're going to make sure to keep that negative sign with it so that we get 800 meters west. So now we have to create our position time graph, and we have to keep the idea that we want the scale to fit what's going on. So we know that we have 160 seconds, and we want to label the key positions that we had. So 30, 60, 90, and 160 are where we personally had our numbers at because that's where the math was easy. And then we're going to look at the shape, or consider the shape of a position and time graph. So are we going to use straight lines or parabolas based on the numbers that we did? So between 0 and 30, we had a constant velocity. Constant velocities mean that we're going to have a straight line. But between 30 and 60, we slow down. And when we slow down, we have an acceleration, but it's negative. So we have a parabola that's going to open up downwards. Then between 60 seconds and 90 seconds, the acceleration is in the negative direction still. So our parabola still opens down. And then between 90 seconds and 160 seconds, we're going back at a constant velocity again, meaning that we have a straight line. So we really have to go through and think and analyze some of this stuff from what we know from our other graphs. So graphing the points that I know that we calculated, I have between 0 and 30, then between 30 and 90, we have a parabola, but it opens downward, and I'm using my position based off of what I calculated back up here. So I went from 600 to 900, and then 600 to 900, there we go, and then back to 600. So I connect those as a parabola that opens up downwards. And then my last calculation gave me 800 meters but west. So that actually means on my graph, since my graph axis is in the east direction, that I'm going to have 800 on the negative portion of the graph. So here are just the key terms from this section. I know it's a little bit intense. We're going to go through a bunch of these examples when I see you in class. But our key terms, our velocity time graph, are going to show us the velocity of an object at any given time. And the area between the graph and the time axis, or x-axis, is going to tell us our position. Now, if it's above the time axis, it's going to be positive. If it's below, it'll be a negative position. And our slope of these graphs is going to give us our acceleration And these are the two area equations we really need to make sure we know, the area of a rectangle and the area of a triangle, because those areas are also going to tell us the position of where we're at. So we are going to run through a couple of these diagrams real fast and make sure that we are on the same point of what is happening here. So when we have a horizontal line on a position or on a velocity time graph, it means it's a constant velocity, which means that our acceleration is 0. Now, if we have this line on the x-axis or on our time axis, that means that our velocity is at 0 for that entire time, so that our object is stopped. If we have a positive slope, our velocity is increasing, meaning that we're accelerating in the positive direction. But if we cross that time axis at all, then we are changing the direction that we are moving. So while this is showing a positive acceleration, we changed directions during that. And then if we are going downwards with our slope, then our velocity is decreasing, meaning that our acceleration is negative, or we are decelerating and slowing down. And again, if we cross that axis, that means that we are now going in the opposite direction. So this is a pretty jam-packed lesson. We're going to do a in-class review on Monday or Tuesday with everything that is going on in here. Or sorry, Thursday, Friday, we'll start it. And then Monday, Tuesday, we'll continue it. You guys will have a quiz actually next Thursday and Friday over graphing.